Alright, what do steel, Poulan, Echo, and Husqvarna all have in common? That's right, they're all brands of chainsaws. And what do chainsaws have to do with mathematics? Logs. That's right. 6-3 is about logarithms. So let's just review a tad bit here. You've got two different forms of the same thing. We've got the exponential form, and we can rewrite that with the whole if and only if statement. So you can basically interchange things between the log form and the exponential form. Sometimes I rewrite it with an arrow. I draw, b to the y equals x. I draw that arrow. The base raised to the exponent equals the argument. We call that thing the argument over here. For instance, 2 to the 5th equals 32. Well, that's the same thing as log base 2 of 32 equals 5. And so you can see how I'm drawing this arrow. Here's my base. Here's my exponent. Here's what it's equal to. Keep in mind that a logarithm is just an exponent. That's it. Nothing more. Logarithms are just exponents. We do have to be careful, or you got to get comfortable with this idea of switching back and forth between these two things. In example 1, we're going to have to evaluate these things. We are not allowed to use a calculator on these. These are no-calc situations. We will eventually have some calculator situations, but this is a no-calc situation. So we've got, we can always rewrite it. I'll always tell you, if you can't solve it as a log, change it to its exponential form. Lots of times in the book, like you'll never see this equals x part. You'll just see log base 5 of 125. You know it has to equal a number, so I always put equals x. Even though the book doesn't put that, I always put it. So 5 to the x power equals 125. Okay? 5 to the x equals 125. Well, 125 is 5 to the 3rd power. Now, if the left side equals the right side and the bases are the same, what do you think the exponents have to be? Equal. So, x has to be equal to 3 in this case. I'll come over here and do the same type of thing. 5 to the x equals square root of 5. Well, that's 5 to the 1/2 power. So, x must be 1/2. 5 to the x power equals 0.04. Oh, that's not so nice. That's 4 hundredths, which is 1/25, which is 1 over 5 squared, or 5 to the -2nd power. Wow. So what does x have to equal? X has to be -2. Had to do a little work there. Maybe bring up some great memories of the past. Okay, how about this next one? Put it on the screen for you. 4 to the x equals 8. Okay, now I don't know how to rewrite 8 as a power of 4, but I do know that 4 and 8 share a common base, so I'm going to rewrite this as 2 squared to the x equals 2 to the 3rd. See how I've rewritten 4 and 8 as powers of 2. So I can, oh look, power of a power property. So that's 2 to the 2x equals 2 to the 3rd. Well, if the left side equals the right side and the bases are the same, then the exponents have to be the same also. 2x must be equal to 3. Therefore, x equals 3/2. Common logs are what base? They are base 10. So if you see something which does not have a base written in, you can assume that it is a common logarithm and it's base 10. So let's see here. 10 to the x equals 1,000. Right, just rewriting that. 10 to the x equals 1,000. Well, 1,000 is 10 to the third. That means x equals 3. 10 to the x equals 1. Right, so all I'm doing is rewriting that, which is equal to 10 to the 0. Therefore, x must be 0. That's true for any base logarithm. Logarithm of 1 is always 0, right? Because it's 10 to the 0. Or log base 17 of 1. Or log base 25 of 1. All of them are equal to 0. Because you're raising that number to the 0 power. That's the only way to get 1. Sorry for yawning. Okay, rewrite it. 10 to the x equals 0.01. Just 1/100. 1 over 10 squared. 10 to the negative second. So x must be a -2. Now when you get to the next example, there is not a way that you can come up with to change 10 or 4 into common bases, or you can't rewrite 10 as a power of 4. So you have to change it to its log form. Convenient that the base is 10, therefore the base of the logarithm will be 10. So you're taking the logarithm of 4. All you're doing is changing it from its exponential form to its log form. And then it's time to punch on a calculator. I know, you thought this day would never come, but it's here. Log 4, 0.602. Can you even see that? Oh, yeah. Now, how do I check and see if my answer is right? Well, 10 to that power. Now I'm going to use the answer button, which is above the little negative sign at the bottom. 10 to that answer should be 4. All I'm doing is going back in and plugging it into the original equation. Yep, I got 4. Okay, must have the right answer. Okay, let's see here. We've another situation where I don't know how to do it. I've got to change it to its exponential form. So 10 to that power equals x. Once again, type it on a machine. 10 to the 3.724. 5,296. Now, you need to understand these two graphs. Y equals 2 to the x. Well, we should know that one, right? That's exponential growth. Asymptote. Y equals 0. Domain, all reals. Range. Y greater than 0, right? Because it can't touch the asymptote. And the graph contains the point 0, 1. Oh. What's this graph look like? What's the relationship between these two things? Well, log base 2 of x equals y. If I rewrite that into its exponential form, I see 2 to the y equals x. How is that related to y equals 2 to the x? Well, it looks like you got x and y switched. The only way that can happen is if they are inverses of each other. Okay, so they're inverses of each other, which means they must be reflections across that line, y equals x. If you reflect this graph across that line, you get a graph that looks like this. So kids get it confused. They get it confused with a square root function, but it's not, right? It's got an asymptote. What's its asymptote? X equals 0, the y-axis. Right? It doesn't come close to that line. I mean, it comes close, but it doesn't touch it. I shouldn't say it doesn't come close. It'd be leading the children astray. Well, the domain, x is greater than 0, and the range, all reals. Oh my goodness, look, the domains and ranges are switched. So if this one contained a point 0, 1, what point do you think this one contains? Yes, 1, 0. Because they've been switched. Now they have some terms that say, they talk about these graphs as strictly increasing or strictly decreasing. I want you to notice that strictly increasing means as you move from left to right through the graph, what's happening to the y values? Are they getting bigger and bigger and bigger, or smaller and smaller and smaller? These are both strictly increasing. Now this one's more obvious. Everybody says this one's strictly increasing. This one, people don't say it's strictly increasing. Why? Because they see it drop off the face of the earth as it goes towards the y-axis. But in all reality, as x gets bigger and bigger and bigger, slowly and surely, it just keeps going up and up and up. So this is strictly increasing, just like the other one. Both of them are strictly. Now, end behavior. As x gets big, these things are both increasing. Sometimes graphs increase, but they have a top level, a top, like a horizontal asymptote, and it never goes past it. That would be increasing up to a boundary mark. But these both increase without bound. Without bound. Because they just keep getting bigger and bigger and bigger. And they never slow down. I'm sorry for yawning so much. I am tired, as you can tell. Have a great day. I hope you didn't fall asleep while listening to my notes. See you tomorrow.